So, welcome. I'm Simon, and I will explain to you superconducting quantum chip design in this video. I'm a young quantum chip designer, and I'd like to share more about quantum chip field. So, what is quantum computer? We start with very simple ones. Quantum computer can perform a task normal computer would take many years to perform, even millions of years, or wouldn't be able to really complete the task. Quantum computers are cooled down to millikelvin temperatures to access superconductivity principles, and the chandelier looks like this. And there are many stages of superconducting or temperature stuff. So we have multiple stages, and in each stage there is different device, mm, different device, right? So here's evolution of quantum computers. Quantum computers evolved from theoretical concepts to first prototypes to usable products. You can see first kind of qubits, which is cavity, which is aluminum cavity, which is designed to have resonant frequency, which is done by creating specific dimensions of the cutout here or gap here, and there is simple transmon placed here. There is kind of silicon or sapphire quantum chip with a very simple Josephson junction here, and this is our transmon really. And on the right side there is kind of very difficult and very complex kind of quantum chip from Google. So there are different types of quantum computers, from neutral atom to superconducting to trapped ion. Uh, each has different properties, and the most advanced one is probably superconducting. Trapped ion is very advanced too. It doesn't require superconducting or cryo temperatures, but it requires a vacuum chamber. And neutral atom, I think, also requires a vacuum chamber. And they have very high fidelity gates, but superconducting is most mature technology, so we will focus on superconducting today. So here is library of quantum chips. You can see different quantum chips here with different number of qubits. You can see quantum chip with transmon pocket qubit uh, with interdigitated qubits, also with star qubits, and also with cross transmons. They're different in the kind of nature, and you can see the transmon pocket has 4 pins and also flux bias. Uh, Interdigitated most of the times won't require flux bias. Star mounts are advanced because they have multiple pins, and they have a squid instead of just junction simple one. And cross transmon are also variation of transmon qubits, which are quite advanced and used for Google kind of processors. So here's my work across different kind of types and domains. So first, let's start with quantum chips, which is at a quantum with which is at the superconducting stage at cryo temperature of 10 millikelvin. There is traveling wave parametric amplifier, which is also at cryo stage, and it also requires 10 millikelvin. And I designed also RF board, which is kind of room temperature board. You can see it. It is gold coated, and it is PCB with some RF there. LNA is low noise amplifier, which is a special type of amplifier used for amplifying signals in quantum computers. And here is a kind of FPGA board, which is used for control electronics types. You can see FPGA here, which is main chip here. You can see RAM memories, you can see flash memories, you can see power circuitry. So here is quantum computer architecture. We start with control electronics, then we go to HAMT, which is high electron mobility transistor, which also requires some cryo cooling. Then we move to traveling wave parametric amplifiers, and then lastly to QPU. Uh, QPU is quantum chip at 10 millikelvin. The traveling wave parametric amplifier is kind of very special type of amplifier, which is at cryo temperatures. You have Josephson junctions there, and most of the time you have array of Josephson junctions, probably thousands of Josephson junctions, and you have capacitors and inductors, and you tune it at a specific frequency. And then you have HEMT transistor, which is simple kind of amplifier with transistors like CMOS process or silicon germanium kind of topology might be B by CMOS, which is kind of between bipolar junction and CMOS type, which is faster for higher frequencies. And then we have control electronics, which is for room temperatures. Uh, so um, this is there is power conversion ratio from dBm to watts. You can see that 10 dBm is 10 milliwatts. And here is power conversion kind of equation here. So Josephson junction, it's a basic element of quantum computers. It is a small kind of device which has two layers of metals, which is aluminum, which becomes superconducting under cryo temperatures. And there is small insulating layer, which is here, and this is an insulator, and it becomes superconducting under cryo temperatures. And you have copper pairs, which are electrons which are paired together and they are close together, and they become superconducting, and they can move at the um, with zero kind of resistance. So there is a squid, which is oftentimes used for measurements, but can also be used for computation. Like I mentioned earlier, it can be used for Starmon qubits. It has two Josephson junctions, and yeah, it has two Josephson junctions, and it's more complex. And one Josephson junction is oftentimes used for biasing with external kind of inductor or transmission line. Here is Josephson junction under microscope. You can see there are different kind of variations of Josephson junctions. Here is first Josephson junctions, which Josephson junction, which is in kind of 90-degree shape, and there is Josephson junction, which is in vertical shape, which is first conductor is below, then there is insulating layer, and there is second conductor, which is now above the insulating layer. So theory of superconductivity, it has perfect DC conductivity. It has tendency to expel magnetic fields, like shown on the picture here. This is superconductor here, and um, an effective wave function that maintains coherence over microscopic dimensions. Um, So this is theory of superconductivity. This is called, I think, Weisner effect or something like this, if I spell it correctly. Here is atom and its energy. So here is how we picture our atom. This is kind of a very nice representation of atom here, and we have atom here which shows electrons here, and with shining light on the atom, we can kind of excite it or push electron to the more excited state, or push to the or give it more energy and push the qubit to the more excited state here, which is shown here. There is this is kind of oscillator which uses Josephson junction instead of inductor. This is called nonlinear oscillator. And here is our Josephson junction symbol, and here is capacitor symbol. You can see that the dotted line is kind of a normal oscillator with mm, inductor lumped element here, and the transmon qubit is the blue line here. You can see the different function which shows that nonlinear oscillator has cosine wave function, and the purpose is that you can reach the most excited state here, or you can reach the state here. Uh, so um, there are kind of um, states, which is first state is here, second state is here, and then there are other states, and there is the effective kind of spacing, which requires you to put energy to put it onto another state. Here is lumped elements representation of qubits. You can see that the normal resonator, which is kind of transmission line and a meander, is shown here as inductor and capacitor in parallel. It forms oscillator here. There is some gate capacitances uh, which are used for kind of coupling. And here is our Josephson junction, which is the rectangle here with the cross. And there is qubit capacitor, which is here, and this forms one transmon qubit. There is kind of representation of qubit here. There is our Josephson junction or squid here. So this is our transmon, and there is transmission line here. The transmission line can be expressed as inductor and capacitor, and it forms a transmission line, and it oftentimes has 50 ohms impedance, which is used for perfect transmission lines because of great performance. So there won't be any reflections at the very high frequencies like 6 gigahertz. So this is used for chip design. There is energy spectrum and energy levels. There is energy in gigahertz and some phase or charge. I'm not sure. Here is energy from junction and energy from capacitor, and you can see the levels are not separated here, so it would create very poor transmons, which wouldn't be resilient to the noise and outer world. There is a bare transmon, and here is our final transmons, which we use in a commercial kind of quantum computers. You can refer to this paper, and you can learn here. If you download the paper, you can read it. So there is just explanation of different elements which are used in quantum computer design. There is resistor, which is constant over frequency in their impedance profile. Now there is capacitor, which is nonlinear over a frequency profile, and there is inductor, which is not constant but is at least linear. So this is inductor. So this is nonlinear oscillator. We already looked at earlier. There is kind of normal oscillator with inductor and capacitor. And here is our transmon qubit, which has Josephson junction here. Mm, you can see it's perfectly separated here. So this is our cosine function because it's nonlinear oscillator. The main and very important element for designing quantum chips is air bridge, which can be used as a shielding. This is the first kind of usage. Uh, and the second one is to connect two islands from each other, or if you have one transmission line in one direction, like vertically or horizontally, uh, and you want to have one that is 90 degrees rotated and needs to go above it, you put air bridge, which is a kind of small bridge here, which is made out of some conductor here. It is quite difficult to really manufacture your air bridge, so you should be careful with your design if you really need ones. Here's coplanar waveguide. What is coplanar waveguide? Coplanar waveguide is transmission line, which is a rectangle. You can see the transmission line here or transmission line here, and it should have 50 ohms impedance. 50 ohms impedance is perfect impedance for high frequency circuits. It is oftentimes used in mobile phones for RF front end, and it is defined by width, uh, spacing, and the ER of material. In our case, it is silicon. So this is coplanar waveguide really. Here is a representation of coplanar waveguide using inductor and capacitor here. So we have coplanar waveguide here and qubit here. So this is our transmission line. Why didn't we need readout resonator? We need so another kind of very important element is meander, which is used as a readout resonator. You can see readout resonator here, and it is used to determine our state of qubit. And depending on the state of qubit, resonance frequency will shift. So it is kind of essential to have your readout resonators, and this way you can really determine your state, and you can know whether it's spin up or spin down. This is a representation of Bloch sphere, and this is how you really determine your state of qubit. So design goals, we want to have as high gate fidelity as possible. Gate fidelity is in percent, and we want to have ideally 100% gate fidelity. So this is quantum error correction. You can see you have your data qubit and you have your measure qubit, and so you have your quantum chip, which has probably hundreds of qubits today. So you have 200 qubits, but to form a logical qubit, you need multiple qubits, and it requires multiple qubits physical to form logical qubit. And you have your measure qubits here, which are blue. And yeah. How do we couple our qubits together? We have multiple kind of types of coupling. We have direct capacitive coupling, which is used between two qubits. which is by capacitor. We have capacitive coupling via coupler. The coupler might be this one, I think. This one is coupler. But oftentimes the qubits are connected and the coupler is to the ground. This is another type of coupling. We have another type which is inductive coupling, uh, which is oftentimes used for kind of fluxonium, I think, because you need your coupling there. Um, so yeah, this is how we couple our qubits together. Another design goal is scalability. Scalability is kind of potential how we really um, scale our qubits up, because if we create a big quantum chip with a lot of qubits, like hundreds of qubits, our chandelier becomes bigger because it requires microwave connections, and these microwave connections are just cables or niobium cables, and each qubit requires uh, kind of a lot of connections, so the chandelier becomes really really big. So this is our quantum computer with hundreds of qubits. So this is the biggest problem with superconducting quantum computers, because the scalability is not that good. For example, photonics quantum chips or quantum photonics, they're very good at scalability, because you might have thousands of qubits, or spin qubits can be silicon spin qubits can be better at scalability. So this is our quantum chip workflow. Now we take our quantum chip from concept, the lumped elements, the circuit simulation, the layout, the FEM simulation, the fabrication. Let's break down the elements or the process here. So concept, it starts with Hamiltonian. Then we create lumped elements, which is like here, Josephson junction, capacitors, and inductors. And this is how we draw our circuits. And we perform our circuit simulation here in some microwave studio, where we actually plug the ports and assign microwave frequencies to this, and really test the resonant frequencies for this. So this is circuit simulation. Then we do layout. Layout is here. And by layout, we are actually at the design stage. So we need to uh, be very careful about our design choices, and whether we want a flip chip or which type of connections, if we want bias, what type of qubits we want to use, um, resonators and meander types, and connections to the ports. So this is really our layout. Then we can move to FEM simulation, which is post-layout simulation, and this is how we actually measure our performance of quantum chip, which is already layouted, and we can really measure the frequency of the qubits, and the simulator will calculate it for us, or we can measure EPR or electric fields of a qubit here. Then we can move to fabrication or GDSI preparation. GDSI is standardized kind of format for creating your chip files, which can be used for manufacturer to really create your quantum chips. So here's layout and description. We have 7-qubit quantum chip with central flux tunable qubit inspired by paper from IBM. So this is really our kind of layout here. You can break it down here. So we have pin ports, pins or ports, and they can be used to connect to the outer world. And this is how we actually wire our quantum chips. Or we put gold wires here to connect with a quantum chip. Mm, and we would have some SMA connectors on a PCB to connect the wires from there to early quantum chip. So here is central tunable qubit, which is here. You can see this is flux pin here, and this is how we can really tune it. So this is central qubit. Here is normal qubit, which has only two connections. Here is coupling bus, like I explained earlier. Here is flux pin, and here is readout resonator, and here is normal qubit. We can attach even some logo or some icon here. So there are different types of processors. First one is cross-transmon, which is a very simple one, which has just junction here at the bottom of the qubit and has connection on top here, and even at the side sometimes. It can be used for, I think, biasing. Interdigitated transmons, there are more advanced ones, uh, which are here. You have your readout resonator here. I think it's readout resonator. Not sure right now. Um, so this is our coupling, really coupling bus here, and you can see this is the type of coupling which goes to ground, which has unconnected pin. And here's another type of kind of qubit. This is transmon pocket, and this is more advanced one because it has more connections. It has four connections. First two are coupling buses, and the second one is readout resonator, and there is also, I think, some flux bias. Also, there is Starmon, which has four coupling buses, one flux bias, and one microwave drive pin, and one readout resonator. And here is our squid, which is two Josephson junctions in parallel, like I mentioned. So here is our cat qubit, which is very specifically designed by one company in France. They're more advanced and they decode kind of quantum information in a different way than normal qubits. And here is our fluxonium, which is developed by MIT in USA, which is most advanced one probably, and it's different type because it's not charge transmon or charge qubit, but it is flux based qubit. So there is how we characterize our qubits. So there is our starmon, and we can break it down to the lumped elements. Here is our transmission line, here is our coupling bus, and here is Josephson junction here, and here is flux bias. You can see that the flux requires inductor, which kind of biases the Josephson junction here. Mm, so this is our Starmon, and here is impedance profile for our Starmon. You can see that there is qubit frequency, there is a frequency of readout resonator, and there is also frequency for coupling bus. So here's our FEM simulation, and this is how we actually simulate our quantum chips. This is some sort of cavity, I think, and there is our very simple transmon or plate with silicon, and there is Josephson junction here. You can see zoomed out Josephson junction here, and there is the process how you actually compute your EPR, but this is quite complex, so I won't cover this. So there are different kind of tools and or different kind of simulation tools. The first one is ANSYS, which is paid and very strong, and it requires deep knowledge to really kind of being able to control it very well. There is Elmer, which is free, lightweight, but there is worse documentation and little bit, very little kind of resources on internet how to use it. So it's not that widely used. And there is Palace, which is developed by AVS, um, um, and it is cloud based and it is very good and it should have good kind of documentation, and it also should have support for PyEPR, which is a tool which is developed by Zlatko Minev. So there are FEM simulation types, and what we actually want to extract from the FEM simulation. So there is first one, which is impedance profiles, which are used for qubits. Mhm. It can be impedance profiles as parameters and stuff like this. Then another type is eigenmode and EPR simulation. Now, here you can extract your kind of behavior of Josephson junction, and you can also simulate electric fields. And here is capacitances. From your circuit, you can also extract parasitic inductances or just inductance of a meander or capacitance of kind of islands from transmon qubit. So this is how you really extract your properties from your circuit. So I made also visualization how Josephson junction is visualized under kind of microscope, because Josephson junction is very small in a few nanometers oftentimes, or micrometers sometimes, um, or probably I would say hundreds of nanometers to be exact. So this is our Josephson junction. So you can see it's 90-degree Josephson junction, and here is first metal, which is on top, and there is second metal, which is aluminum, and it is on bottom. And there is insulating barrier, which is here. This is insulating layer, which is some aluminum dioxide, and there is substrate, which is either silicon or sapphire. We want to use silicon or sapphire because it is compatible with our current kind of processes, how we manufacture our classical chips. So we don't need to really retool our foundries, and we don't need to develop new processes how to manufacture quantum chips. So this is very convenient. So there is fabrication process. The first one is we have our wafer, which is a plain wafer from silicon, and we want to spin coat it with photoresist, and while it is spinning at the uh, very high kind of RPM, probably 9,000 RPM. Uh, we want to cover it with photoresist, so with uniform layer of photoresist. Then we want to expose it to EUV, and this is how we actually pattern it. And this is used with the ASML. Most of the times ASML UVs, because there are more advanced ones. And then we want to develop it, which is with some development acid. Then we want to etch it, and then we want to coat it and then metal fill it. So there are fabrication foundries. First one is Global Foundries, which is the biggest one, and they support Josephson junction and superconducting quantum chips. Now, then there is some university fabs or laboratories like UTech, which is I think this is Netherlands. Then there is Skywater, which is USA, and it was recently being acquired by IonQ. So there are two papers which we can follow. I might attach links in the comments there. So there are some papers. Also, another very important part is traveling with parametric amplifiers and RFICs. We can see RFIC here and traveling with parametric amplifier here. Here is a Smith chart. This is how we actually kind of measure our RFICs and traveling with parametric amplifiers. We measure impedance there, which on top is inductive, and on the bottom there is capacitive impedance. Uh, Here is open circuit, and here is short circuit, and here is our 50 ohm impedance. And you can see that if we go sweep from frequency, it will do our trace for us, so it won't be kind of 50 ohms impedance at all times. So there is one cell for traveling with parametric amplifiers. Here's Josephson parametric amplifier, which is uh, just one Josephson junction, and it is oftentimes tuned at just one frequency. So there is peak it, in S parameters at one frequencies, probably 4 or 6 gigahertz, and there is one big meander there, and oftentimes there is flux bias or pumping our flux here using some external bias or inductor or trace, whatever it is. So there is traveling wave parametric amplifier here, and like I told you earlier, there are many cells, probably thousands of them, and there is kind of scheme or array or repeated kind of pattern, which is one Josephson junction, capacitor, some resonator or capacitor and inductor here in parallel, and capacitor here. And we can see zoomed out one cell here. We can see Josephson junction probably here, somewhere over here. There's a big capacitor, and there is some inductor here. So this is under microscope, and there is first cell here. So there is also RFIC chip, which also sits at cryo temperatures. This is our HEMT or RFIC, and here is our CMOS LNA here. We can see inductors. Those are big inductors here. There is first kind of transistor here, which is some CMOS transistor probably. Second one is here, third one is here, and fourth one is here. So this is our RFIC LNA. There is more advanced CMOS LNA here, which has more capacitors, inductors, and transistors here. Very very important part of RFIC are on-chip inductors, because they are used in RF designs, and in digital or very simple analog designs, the inductor are not used because they are not tuned at the frequencies. But if you go up in a frequency, few hundred megahertz, or probably just gigahertz and above should be fine for our inductors. So this is where we use really our inductors. So in frequencies above 1 gigahertz, I would say. So here is on-chip inductors explanation. There are different kind of types, and they can be either rectangular or this special kind of shape here. and it might be even differential. And this is, I think, some kind of transformer. Yeah, it is transformer. It is called balloon, and it is for mm, kind of converting to 50 ohms impedance, I think. There are different types of transistors which are used for RFIC LNAs. There is bipolar, which is very simple. Uh, when they are small, they can be used for quite high frequency LNA, but they're not very widely used. CMOS is newer technology. It has a lot of parasitic capacitances here, and can be used for high frequencies, but oftentimes they're used for power amplifiers. And there is most advanced technology, which is combination of bipolar and CMOS technology, which is very popular for very high frequencies. And there is combination of both worlds, and it is oftentimes used with silicon germanium process. There is evolution of MOSFET technology. We won't cover this one probably. There is a third order intercept point, which is very important for amplifiers, and this is how you actually measure the properties or of amplifier. And this is, there is linear kind of region, and there is third order intercept here, and where, well, this is linear region, I think. And there is a third order intercept, which tells us that it won't be amplifying the signals, and it will start surpassing the gain, and also the noise will be higher, I think. So this is last slide here. Thank you very much. So
Yeah. And you also had a like workshop portion prepared where you would walk through some like either notebook or
sure.
something. Do you want to go
Yeah,
through that?
sure. So we would continue straight away.
Yeah, I think we can just continue to it if that's good for you.
Yeah, sure. I thought there might be some questions, so I wanted to answer a few questions there. So if there are any questions, I might be,
Sure. Yeah.
or if
I have
not,
a question actually. So I saw earlier, like towards the end, you showed a lot of um
RS stuff.
how they fabricate inductors. But I know
Mhm.
at least in some, because I was in a spin qubit, like semiconducting qubit lab before, and I know sometimes they just directly put inductor parts bits, so the ones that are, I guess, like currently already manufactured for computers, like those kind of bits, they put it directly onto their board as like the inductance component. So I'm curious, like, what's the benefit of having to like manufacture those specific inductance loops on like the chip circuit? Because then I remember a couple of those designs, they're very complicated, and also you have to use the air bridge, which you said earlier is very annoying to fabricate.
Yeah. Yeah, there are probably different types. So the QPU, they use meanders, which is kind of, the inductance is hidden there in a meander. And for RFIC, CMOS LNA, those are not QPU, those are not quantum chips, those are amplifiers. So they are different in nature, and they require inductors there. So this is a different thing, kind of. And quantum chips are different in nature. So quantum chips have juice injections and meanders and readout resonators, and um, they won't require probably fluxonium. They have some small array of inductors there, but this is a very special type of kind of qubit. So they have, yeah, hopefully that answers your question. Thank you for it. So I'll jump to the notebook here. So this is our, hopefully you can see it.
Yeah, we can see it.
Sure. So here's our Jupyter notebook. We need to install a Qiskit Metal first, and then we can run examples here. So this is our Jupyter notebook. First, there is
So actually,
some
Simon, just a quick question. So for this notebook, do you plan to share any like notebook with the audience, or is most of it just going to be like a walkthrough? Like, can you maybe send this notebook to us?
Yeah, sure. Give me a minute. I'll just find it. Um, I think it's called tutorials, and I think it's here, so I can send you a link.
Thank you.
So this is really, mm, so this is our notebook here. First, we need to import a Qiskit Metal. We need to import design, draw, and some dictionaries here. It's also NumPy, collections. This is not really interesting. We need to import the stuff here to really get started. Then we really define our design. We create a GUI here, and then we enable override function. So we don't need to delete it if we really draw different qubit on top of our current one. So we can run this example. Now it launches Qiskit Metal for us. We can see blank page here. I'll put it on split screen here. So this is our Qiskit Metal here. Now we need to import some components here. We can see transmon pocket here. We can see root meander. We can see route anchors. We can see route pathfinder, open to ground, launchpad wire bond, and stuff like this. Um, so there are design variables. There is chip size, which will define how big our plane of quantum chip is. It is in millimeters, and it is 9 millimeters to 6.5 millimeters. So we can run this too. It won't do anything here. It will appear once we create our GDS file here in Qiskit Metal, and we can do this by clicking GDS
Okay,
once we have
Simon.
our own. Uh-huh.
So I think some people in person need a moment to get onto this notebook. So maybe if you could
Uh-huh.
wait a minute or two. Sorry about
Sure.
this. Yeah.
Sure.
Uh, and maybe if anyone in Zoom also needs some time to follow along, just let us know when you're ready if you want to also like open up this notebook.
So, are they ready already?
So we can ask. So on Zoom, do you guys need another minute or two? Do you have the like notebook pulled up if you want to follow along? Maybe you can raise your hand and just send a message if you still need some time. Okay, let me just check in with in-person people. Just one more minute, Simon.
All right. Sure. It's very simple. You can just execute the commands by clicking Shift and Enter, and it will open up Qiskit Metal for you, and you can really design stuff there.
Yeah, we can go ahead now, Simon.
So there is another kind of function called Transform Pocket, and we can get template options from here, and we can see the basic parameters here as position, x, y, and orientation, layer, connection paths, pad width. By changing pad width, we would change actual properties of transmon here. So we execute it. And now we create dictionary where we define our kind of orientation, and we define the basic connection paths for transmon qubit here. It won't create actual qubit right now. You can see the page is blank here. But now we actually create transmon qubits here. So you can see we have actual transmon qubits here. And now we can open the Qiskit Metal and play with this for a little while. So we can, here at the Q components here, we can select our transmon pockets here. So this is really window for choosing your devices. Here there are parameters for transmon pocket here. There is position x, y, orientation. By changing orientation to it is in 90 degrees, so in degrees. So we can see our transmon changed. So here we can actually change the parameters here. Here is our library of, by clicking this icon, toolbar, we can see different kind of components there we have. By clicking there, we might pick up mm, the qubit here, and we need to click create to actually put it onto our workspace here. So there are our devices here. There are here in this toolbar with the hand. There is our devices. There is some scripting of the devices. I think I've never used this one, to be honest. There are some features we can do. We can either load design or we can save it. If we save it as my design metal. By saving it, we actually create a Python file here, which is we need to open it with some editor notepad, and it will create some file here for us where the components are defined. So this is very useful if you change your parameters in here. so it won't get projected to the notebook in Jupyter Notebook. So you might need to create a Python file and manually put the files or created created content from here to the Jupyter Notebook. So this is probably very simply said how to. We can also zoom. Can not sure, honestly. There is also a ruler, which doesn't work. I'm not sure. We can also rebuild our circuit, which will rebuild it if we do any changes and want do a rebuild and auto scale here, so we can rebuild it. We can create GDSI files here. We can export it to HFSS, which is ANSYS, or Q3D, which is for capacitive extraction. This should be kind of it. So we can now focus on our qubits here, and we can change the pad gap, and it will change the gap between the islands of a transmon. So we want to say 30. So this is we can change the inductor width, which is kind of Josephson junction here, I think. We can change the pad width and pad height. This should be this one. So let's go for 600. Yeah. Oh no, it's the island here also. We can change the pocket, which is the gray box here, which is where the ground or ground from metal won't be there. So let's say, I think 600 it was. No. So we can play with the parameters here. Is there anything more exciting here? No. We can also change the this transmission line here, and we can change the orientation of the pins here. We won't do this one, I think. So let's jump to the Jupyter Notebook again. And now we want to play with meanders. So we define a meander here, and we create some basic parameters here like fillet, which says how rounded our meander will be, and it will also say leads, which is start straight and end straight. Those are leads, and now we actually create dictionary, and now we actually create our meanders here. So leads are from this point, from pin here, and the fillet is how rounded our meander is. And if we click route meander, we can change the fillet here, which might be you can see it won't do any rounded because it's the number is too high. But if we say 50, it won't be as rounded as here. So this is fillet. There is total length, which will determine how big our meander is here. So this is our bigger meander because of length. And this is it, probably, yeah, for meander. Very simple one. We have our pin ports, which are here. There are just very few values like position. If we change position here, the port is here. If we change position to 2000, it will put it here probably. Yeah, 2000. You can see 2000 here. We can change the position of Y, which is 4000 here. So we can see the port is so the port is here. We can also change the orientation. You can see the current orientation is like this, and we can change it to 90 degrees, which is like this. We can also change the lead length, which might be probably 70, and it will increase the length here. So now we need to execute it again to rewrite it. So those are our pins, and now it will start to get really exciting, I think. So here are more advanced meanders here, or very similar ones, probably similar ones. So the length is here, the fillet is here, and this is all we need to care about. So it's here. Now it will start to get interesting because we have our route anchors, and so this is our route anchor, and we can define points of the anchor here. So this is our first point, there is our second point, and we can do this by creating a kind of array or jogs here. We can change the jog type, which will probably change the um, the angle. It will change the angle. We might do a 45-degree angle here, and there is our point. There is our point here, and we have first point, which is 2, and 2 minus 5, which is here. So the first point is here, and we define our x value here and y value here. So this is our first anchor, and we need to connect our uh, kind of qubit port here. So we define our qubit here, and we define our port here, and we also need to define a different or second port here, which is port called P to C, and it's called tie, so it's here. This is called end. And then we need to define our lead, which is how far from the beginning we want to make it curved here, or this is the mm, how we um, start straight. So this is the place here. So this is all we need to really do. So this is our quantum chip here. What we can do now is we can open ANSYS and we can import the design here. So to show you the features, uh, we first need to create project, which is by clicking new project, HFSS, and HFSS is here, and it will create a work environment here for us. So this is HFSS, and we can export it like this. We can select all the components, or we can uncheck some of these components if we want to export the whole chip. And this is not really important here. So we can click confirm selection and render, and it will render our quantum chip into ANSYS like this. So here's our quantum chip, and here's some bounding box here. We can delete this for now. And if we rotate it here, here is our quantum chip here. So there is some silicon substrate here, which is here, and here is our rendered kind of preview of quantum chip. Mm, it's very simple. So we can close this, or just it won't close the ANSYS because this Qiskit metal is still open. So now we can generate GDSI files, which is very simple by clicking GDSI, and we need to define our ground plane as true. And now we can browse, and call it my QDesign, save it, and export, and it will export our GDSI files. So now it's exported, and now we can open it. We can open it in any kind of tool we want, and this is our GDSI preview. We can see the dimensions here are 6 millimeters by 9 millimeters. Here is our ground plane, and here is our uh, transmon. So very simple. So now we were quite I would say, quite. We went through the materials quite quickly. So, would you like to maybe say another example?
Yeah, I think that could be valuable, Simon. Um, Maybe you could walk us through a bit of your like workflow if you think you would be able to do that right now, because I know you didn't plan this, but like maybe in HFSS or some of these other softwares, and just speak a little bit about what the FEM simulation actually looks like, what you look for, how you're designing a chip, just some like higher level stuff. And um, yeah, do you think you could do
Yeah,
that?
sure.
Okay.
Sure. I'll go through simulation. I can even do more advanced kind of chip to preview simulation. So give me a few seconds. I'll just close this one. Let me just open it, and in a minute I will. So here is our more advanced kind of quantum chip, which we can very quickly skip just to give you preview. So we can focus here on really exporting our quantum chip to ANSYS and performing EPR here. And so here, or we can, in this kind of point, we create our logo here. And it looks like, let me wait for it to render properly. It will take a little while because there is uh, image import function there, which takes a little time, so it will need a little time. So in the meanwhile, in the meantime, we can take a look at the function to early run our simulation like EPR. And so here we design or we define our PyEPR import here, which is tool to run EPR. Now it should be, yeah, it is here. So there is our quantum chip. Now we need to perform some stuff here or run our example. So this is how we run our PyPR. We need to define some stuff here, import stuff, and we need to, from Qiskit metal, import EPR analysis and define our design and select HFSS. And then we need to do HF start. It will start HFSS for us, which is ANSYS. So now we have our ANSYS opened by script. You can also control ANSYS by script. And now we can really activate our design. So it will open our transmon design. It will call it transmon readout. And by the way, you can find the similar kind of setup for render simulation on a Qiskit Metal page too. So you can run your simulation too. So we need to render our design to HFSS. So this line is to render it. Are there any questions? No.
Yeah, I did have a quick question. Can you hear me?
Yeah, sure.
Yeah,
Go
I
ahead.
was wondering, from the GDS file, how do you end up doing the nice Blender rendering? Is that a complicated process?
Uh, yeah, I would say it's quite complicated because you need to kind of import it to the files like mm, it's some cat tool where you need to import your GDSI files. Then you need to import it to Blender, and from this, you need to really define your materials. You need to create some plane for the renderer, and then you need to set up lighting. You need to set up camera, uh, and then you can do realistic renders like this.
Okay, awesome. Thank you.
No worries. So here is actually our um, what worries me is that it's not rounded like this, but it should be fine. We can simulate the other ones. It's probably some bug in my code that it won't render the rounded ones. So, um, but normally it works for me. I don't know why it's not working right now. So here's our quantum chip here, and we can run our simulation here. So here we define our some parameters for simulation, and here is variables like inductor value for Josephson junction and parasitic or capacitances of Josephson junction. We want to have large inductor because Josephson junction acts as a large inductor in the simulation to compute electric fields. So we add 20 nanohenry, which is very large one. If we compare it to normal inductor, it would be very large inductor, but Josephson junction is very small, thin wire. So we set up passes here in number of modes, and then we let it compute. You can see it takes some time to analyze our render here.
The one thing that might be helpful is if you could explain what EPR is, what it means. I don't know if everyone
Uh,
knows that.
this is a tool how to uh, or like this is uh, this is paper from a long time ago, but in our case, it is tool how to actually compute some parameters of Josephson junction. And if we run our EPR, we can actually find energy of Josephson junction. We can find kind of all the necessary parameters, which I will show once it will run. Hopefully that answers your questions. So probably it should be so here we have our Josephson junctions. If we zoom in for the right one, we can see rectangle of Josephson junction. I'm not sure which one is it. Or just this will, yeah. So this is rectangle number Q3. So this is our Josephson junction. There is a short line which sets the direction and kind of measures the length of the Josephson junction, and it helps EPR to compute all the necessary parameters there. Here is kind of all the components which are perfect conductor here. So the perfect conductor is everything green. You can see the ground plane is perfect conductor because the ground plane is simply aluminum, and so this is really our ground. The pads are also aluminum, and the Josephson junction is aluminum too, but there is thin insulating barrier. We substituted with just a rectangle here, and here if we click here on vacuum, we need to define our vacuum here, which is used for computation too. So this is kind of like cavity mode vacuum box here. And here is our substrate, which is silicon. You can see this is a box like this, and by clicking main, probably we can assign material, and we can, from this we can pick either silicon or we can go with sapphire. We can click the material and we can change it, but this is not really recommended once our simulation is running. So we shouldn't really change the values once the simulation is running. For the aluminum, we don't need to assign our material. All we need to do is to click like this. I'll select the assign boundary and perfect E, which will set a perfect conductor for us, which is superconducting material, so it won't have any resistance, and this is caused by the effect that it is cooled down to millikelvin temperatures, and hopefully it will compute something for us. Or what else we can do? We can really skip the EPR simulation, and we can really delete our Josephson junction rectangles there. now to have just one Josephson junction rectangle, so it will compute just one, and you won't need to run whole simulation because I'm not sure how long it might be able to run the simulation. It might even take um, feet, like tens of minutes. So, but this is really important to run it because by this we can see the um, just injection. What we can do is we can jump to Qiskit Metal and we can open a new kind of file. Um, we can open the SQBit one more time. We can run just to create our layout, and from the layout we can jump to ANSYS because it requires to open the ANSYS from Qiskit Metal to actually perform as parameters and to be able to assign uh, pin ports for simulations to calculate S parameters and the impedance profiles. And also from this, we can also calculate capacitances.
While this is running, could I ask a few questions?
Yeah, sure.
One question I had was, um, so what is making like using Qiskit metal or quantum metal easier than just whatever previous software or software people use to design circuits?
It's easier because um, it's open source. The first very important stuff or very important thing is that it is open source, and it's very fast and easy. And the previous softwares were probably Keysight or Cadence, or it might be also created in ANSYS if you play with the primitives and draw the circuit from scratch up. So mm, it is very simple, very easy, reliable, open source, and it is Python based also, so you can really modify your script. It is highly modifiable, so you can add your stuff. You can add kind of functions, new functions. You can um, mm, you can um, play with this.
Okay. Um, so if I was to briefly summarize like the purpose of, I guess, Qiskit meta and also like what we're doing today in general, um, we want to use Qiskit meta so we can easily design circuits that we can plug into some simulation software so we can understand some parameters that we can operate the qubits at.
Yeah, exactly.
Okay.
Uh, so would you like me to elaborate on this?
Yeah,
Uh,
sure.
so very simply, we design our layout simulation, or we don't need anything, just Python file, and from this we can export it to ANSYS, and we can really verify the post-layout simulation by running KPR. It is very convenient because we don't want to really fabricate our quantum chip and without knowing its parameters, because we at least want to verify the parameters for meanders, because it is very important. The frequencies are very important if the layout is correct and the calculation of the ports is correct, so we can have the correct resonance frequency for our resonators, so we can really uh, drive our qubit with the correct frequency. And also the qubit has its own frequency, so we want to really find the correct frequency for our qubit uh, to read it with resonator. And also there are couplers. So this is coupler from one kind of qubit to another, but there are couplers which are connected to the ground. They're also very important, and you need to measure the properties too. So you need to simulate it in a post layout tool like this. So this is very important.
You talked a little bit earlier about the workflow of designing. I mean, just working through designing a project like this, where, you know, at the beginning you have to consider the Hamiltonians, and then later you package them into some components. So I was wondering, in that stage, um, where you have to in this stage where you take the various components that we know, and then design that into some larger circuit uh, or device. Do you have to consider or do any calculations at that point, or is it more using the just knowledge of the properties of the components that you already created or understand?
Yeah, so you're basically asking if you have your prior um, kind of knowledge about component values and how you design your quantum chips in circuit simulation, all right? So, yeah, basically this iteration process, you can have your workflow which is horizontal and from one point, but this requires a lot of experience. And once you design probably hundreds or tens of different quantum chips, you will get this experience. So you might be able to really pass the values from the first run. But if you're a little more unexperienced, it might be iteration process where you go from layout back to the circuit simulation, and you kind of tune your values and play with the knobs and kind of adjust your kind of parameters. So um, this is what we do.
Okay, I'm gonna sit down. Thank you for answering.
No worries. You're always welcome.
I also have a question.
All right, sure, go ahead.
So I'm curious, it looks like what you do is mostly you design the circuit in the QSIG metal and then you export it either to HFSS or GSD programs, like other programs. And I know like ANSYS is really powerful. I'm curious, is the QSIG metal really just like limited to it makes designing the circuit part easier, or is it able to also cover some of the ANSYS capabilities?
Um, I mean, Qiskit is really powerful for designing for designing mm, quantum chips, and you can do this using your Python file.
Mm-hmm.
And I think the capabilities of ANSYS are not that wide to really design very complex quantum chips, because it requires to have meanders. What I was trying to say previously was that you might be able to, using ANSYS, do some very example or very simple kind of quantum fixtures or quantum chips, like the one I showed with the cavity, where there was just silicon, some silicon chip, and there was just Josephson junction. So it was very simple. There was three rectangles, so you wouldn't use Qiskit metal. You would probably design it in ANSYS, and you can also export it. But for very complex quantum chips with qubit counts of tens of qubits, or um, even hundreds of qubits you can design in your Qiskit mill. Uh, you wouldn't use your ANSYS probably.
So you probably would like simulate how the qubit system works in Qiskit metal, and the answers part is more for like if you have one or two smaller qubit system and you can take a look.
No, Qiskit metal is pure design, kind of. Qiskit metal is used for designing quantum chips, and
Oh,
ANSYS is for simulating quantum chips.
I see. Okay, thank you.
No worries. So now I can share again because I have my Qiskit metal here, and what I can do is I can open a new project hopefully, and I can open HFSS from scratch, and I can probably import the render again, and it will render it. And once we have it rendered, we might be able to assign ports, and from this we can simulate our S parameters. I can show you how to set up frequencies and mm, how to simulate our ports. Hopefully it will complete until it's end of the session, because it takes really a lot of time if you have more advanced qubits or quantum chips. It will take a lot of time because it will have probably 5 qubits to compute, or in our case 7 qubits. So it's more difficult for the simulation software to complete it. um, Hopefully I learned, or I um, taught you um, um, how to design quantum chips in Qiskit metal, and kind of simulation is a nice addition to um, kind of workshop. So we will see if it will complete. Do you have any other questions?
I can ask another question if I thought Laura was gonna go, but um, so when you have to go from the this initial testing stage to this fabrication stage,
Mhm.
is it much more complicated than just exporting the GDS from Qiskit Metal?
Oh yeah, if you want to actually design your quantum chip, uh, it is you need to know some parameters, like which kind of foundry you have. But basically, it's very simple. What you need to do is just import or export the uh, GDSI files, and open it in some editor, and add Josephson junction in some editor, because Qiskit Metal probably won't add the Josephson junction there in our qubits, because every foundry should have specific parameters for Josephson junctions. So it's I mean, Qiskit Metal is general tool, and it is not tied to any PDK. Also, if you have your foundry, you need to have very specific Josephson junction. So you might want to import it into K layout or some tools like this, or which is GDS viewer, and just manually draw rectangles, which are Josephson junctions. So it's a little bit more complicated, but it's very simple as well.
But does the Qiskit metal, like when you import Josephson junction, is it actually uh like Josephson's junction, or is it just a representative and then it
I
has some
think,
similar properties?
yeah, I think Kiskin metal creates little kind of rectangles like this, which is just representation, and it is here for simulation. And actual Josephson junction should have like two metal layers, which is first one is bottom, second one is top, and there is small insulating layer uh, in the middle. So yeah,
Okay, thank you.
no worries. So now we can really see our meander here. So this is our meander. We need to create a rectangle here, which is our first port. We need to assign port, lump port, add integration line, and add 50 ohm impedance. So this is our first port. Second port is here. Um, port, lump port. So this is our second port. And now we can actually go to analysis, setup, and or we need to add solution setup, auto, and we need to create more points. So more points, more time it requires to compute it. So this is 4,000 points, and from 0 gigahertz to 10 gigahertz. And so this is our setup. And now we need to go to results, create model data report, and create as parameters and as parameters for sweep and a new report. So it will create graph for us, or parameter plot here. And from here, we can go and analyze all. You will need to save the project, and it will take a special time to really compute it again more, because the ANSYS is already working on our previous example, so it won't be just now. So this is how we actually measure our S parameters and how to set up our simulation. You have any other questions in the meantime?
Also, just so you know, we kind of wrap up after this part is done. I think once it gets to like 12 local time, so in a few minutes, we can just call it there. So whenever you find a good stopping point.
Right. So mm, you won't probably finish the simulation here, so I would probably end it here.
Sure.
So thank you very much for your attention, and thank you very much for inviting me, because UCLA is a very prestige organization and very prestige US school. So it was my big honor to be there. Thank you.
Yeah, of course. Thanks for the great talking work back, Simon.
No worries.
Okay. Any final questions, or I think we're all good in person. So yeah, thank you again, Simon.
All right. Thank you for inviting me.
Of course.